Hi, welcome back to my channel. For today's video, we will continue with the video that we have done for the intuitive and formal definition of a limit of a function. And by those formal definition, we will have to discuss basic limit theorems for solving functions. So by this, I will also have to show proofs for the theorems on the limit of functions. In that way, we will be able to make sure that we can assure that the theorems that we have discussed are actually correct and valid. So I will provide you the proof for that. Of course, technically, because we're talking about math, so we're also talking about proof of claims. So for those who are new to my channel, please don't forget to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon. And for those who have been here for a very long time, thank you so much for your undying support. And I would just like to let you know that the purpose of this video is because I really want to help for the online classes set up in this new normal. So I call this as new, mathematics for the new normal. So I just want to help. So if you have clarifications, don't hesitate to comment down there so that I would know and we can also discuss things like that. And if you have any requests for specific topics in math that you would like me to discuss here, yeah, you can comment down there so that we'll have to discuss that on my next video. So enjoy watching and let's start now. Okay, so we will start now for the basic limits of, okay, so we will start now for the basic theorems for the limit of a function. So let's start with the first theorem, the uniqueness of the limit. So what does this theorem imply? This theorem says that if you have the limit of a function f of x and this f of x approaches a, you have L1 and the limit of f of x also at the same time as x approaches a is L2, then this simply tells us that L1 is equal to L2. Okay, so it means to say that for instance, if you have let's say limit of f of x as x approaches 20 and that's equal to 50, then you wouldn't be able to find another value aside from 50 that would give the limit of f of x as x approaches 20. So that means to say that this is just the limit and that's all. Okay, so to make sure that the theorem here is actually true, so we will provide a proof for this. So okay, throughout this proof we assume that the function maps from x to y. So this is your domain here and this is your range. I'm sorry, the codomain rather. Okay, so if the limit of your f of x as x approaches a is L1, then you have an epsilon 1, and for this time we don't know yet what the value of our epsilon 1 is, so meaning to say that we will make an adjustment later. So that's technically the technique on proving the limit of a function. So we don't know the value of the epsilon 1 here, and in this case for some delta 1 greater than 0, you would have the x coming from your domain, and of course you'd get this inequality. This is based from the formal definition of the limit of a function. Then what happened? Then your f of x minus L1 here is less than epsilon. So the absolute value of f of x minus L1 is less than epsilon 1 rather. So on a similar way, if the limit of f of x as x approaches a is also L2, Then same thing happened. You have epsilon 2. In this case, we also don't know what the epsilon 2 is. Now for some delta 2 greater than 0, x in the domain, and 0 less than x minus a less than delta 2. Then you would also have this way. Okay, so if we let this one here, no, we're actually solving rather. So we solve for the L1 minus L2 here. And our goal, by the way, remember this is our goal, to show that L1 and L2 here is equal, to make sure that if they are equal, it actually implies that the limit of the function is actually unique. So here, in this case, remember that L1 minus L2, inside the absolute value, I can put 0 on it. So nothing will be changed. So if I'm going to put the 0 on it, it's like adding negative f of x plus f of x. So remember the sum of these two is 0 minus L2. And technically, by triangle inequality, I can pair this as L1 minus f of x and plus f of x minus L2. This is simply the same as f of x minus L1 because this is actually inside the absolute value sign. So basically, L1 minus f of x is less than epsilon 1. Remember, this is less than epsilon 1, and f of x minus L2, that's epsilon 2. So remember that when we prove the limit of a function, we're actually having the end point the end step as less than epsilon. So the idea is if you're actually adding the two epsilons, so we will know that this is epsilon over 2, this is also epsilon over 2. In this case, this is epsilon over 2, this is epsilon over 2. In that way, this one here is less than epsilon over 2, and this is less than epsilon over 2. That is equal to epsilon. Okay, so since epsilon is arbitrary, then we would end up having a contradiction. So in this case, the L1 and L2 here is equal. So that proves to us that the limit is actually unique. So if you have any questions or clarification, please comment down there so that I would know, and in that way we will be able to discuss on the next video for that. So technically this is the proof of the uniqueness of a limit of a function. That's it. Okay, so the next theorem that we will have to study is the limit of a linear function. So this is the limit of a linear function. So remember that a linear function is of the form f of x equals mx plus b. Okay, so in this case, the limit of a linear function says that if given you have two functions, so let's say you have b and c to be constants, so any arbitrary value from the real number, then it simply tells us that the limit of bx plus c as x approaches a is technically ba plus c. So it simply tells us that you just have to substitute a to the value of x here, and that will be the limit of your linear function. Okay, now I'm gonna show you the outline for this. So observe that if bx plus c, the absolute value minus the ba plus c. So remember this is f of x here. So this is just the f of x minus the limit L. So in this case, we will have to subtract f of x minus L here. And technically, this is the same as b x minus a, and so this is equal to b times the absolute value of x minus a. So in this case, our goal here is that bx minus a, so this is our goal, to be less than epsilon whenever this is 0 less than x minus a, the absolute value for that, and then less than delta. Okay? This is equivalently the same as x minus a less than epsilon over b whenever 0 less than the absolute value of x minus a less than delta. So what are we gonna do? We have the idea here. We can choose our delta to be equal to epsilon over b. So in this case, if our delta here is less than epsilon over b, so it simply gives us the idea that this is b x minus a, this is less than b times epsilon over b, and so this is equal to epsilon, which shows that this is already the limit of a function. That's it. Okay, so we will consider example for that. So suppose we are interested to look for the limit. Let's think of a linear function that's 3x plus 1 as x approaches 0. So technically, you just have to substitute your a here, which is the 0, on your x. So that's 3 times 0 plus 1. So you'd get 1. So that's the limit of 3x plus 1 as x approaches 0. Also, let's say 7x minus 5. So this is a linear function. So x equals approaches 0. So you would get negative 5. So this theorem also only holds when the function is linear. Let's say we have another, the limit of 4x minus 2 as x approaches 1. So this is 2. That's it. So by having a discussion on the limit of a linear function, we would have a corollary for that. So corollary 1, this is what we call the limit of a constant function. Limit of a constant function. So the limit of the constant function simply tells us that if c is constant, then for all a in R, the limit of c as x approaches a, so that means to say this is constant, is always c. So say for example, the limit of 5 as x approaches 1 million, this is always 5, so because you take the constant here. The limit of 20 as x approaches negative 5, that's also 20. So you only have to take the limit because that's a constant function. Now, second corollary from the theorem on the limit of a linear function is that the limit of identity function So the limit of identity function simply tells us that for every a in R, so that means for every real number a, the limit of x as x approaches a is a. So example, what's the limit of x as x approaches 20? And that's equal to 20. That's it. Okay, so technically speaking, the reason why these two limit theorems, the limit of a constant function, the limit of identity functions, are actually corollaries to the limit of the linear function is because if you notice, your linear function is of the form mx plus b. So this one is actually a identity function. This one here is actually a constant function. So technically they're coming here, sorry. This one is a identity function. So technically they're both coming from the linear function. So I'm going to show the proof for that. For number 2, this is very obvious. You can just assume that your f of x, mx plus b here, you assume that b here is 0. So you get to work on this one. So for letter C, the outline of the proof for that is that, of course, you let epsilon greater than 0. So we need to show that we can find a delta greater than 0 so that your f of x minus c is less than epsilon whenever 0 less than the absolute value of x minus a less than delta. Observe that this inequality here is trivially satisfied for all x. Why? Technically, because your f of x here is actually the c. So basically, c minus c is 0. And technically, that's epsilon greater than 0 on our assumption. Which means to say that that's trivial proof. Just a pretty basic on proving the limit of a constant function. So that's it. So, okay, so the next theorem that I have to discuss is the limit of a sum of two functions. So, what does the limit say about this? So what does the theorem say about this? It says here that if the limit of f of x as x approaches a is, let's say, L, and the limit of g of x, so you have another function g of x as x approaches a is m, then it says here that the limit of the sum of f of x plus g of x as x approaches a is the same as the limit of f of x as x approaches a plus the limit of g of x as x approaches a, and that's technically L plus m. So meaning to say that the theorem says that the limit of the sum of two functions is actually the sum of the limit of functions. That's it. Now, because of this theorem, we would end up having a generalization for that, meaning to say that by the aids of mathematical induction, you would be able to achieve that if, suppose, for example, you have the limit of f1 of x, so that's the first function as x approaches a, and let's assume that the limit for that is L1. You also have the limit of f2 of x as x approaches a, and that's L2, and so on up until you get the limit of fn of x as x approaches a, and that's equal to Ln. Then it says here that the limit of the sum of fi of x, I from 1 to n as x approaches a, is the same as the summation of the Li I from 1 to n. So technically, the limit of the sums of these n functions is technically the sum of the n sums of those limits. That's it. So to make sure that the theorem is true, I'm going to erase first the generalized theorem for the limit of sums. So because technically this will be gotten when we are able to prove that the theorem above is actually true, then by the aids of mathematical induction, this following theorem is also true. Now, to make sure that this theorem here is true, I'm going to show the proof for that. Okay. So let epsilon be greater than 0. So remember, if the limit of f of x as x approaches a is L, and also the limit of g of x as x approaches a is also M, then there exists, of course, then there exists delta 1 and delta 2 greater than 0 such that um, the absolute value of f of x minus, what's the limit? That's L, is less than epsilon over 2. And the absolute value of g of x minus, what's the limit? That's M, is also less than epsilon over 2. This is whenever 0 less than absolute value of x minus a less than delta 1. And this is also whenever 0 less than x minus a less than delta 2. So by this, you do have two deltas. So I'm going to take what's the minimum for that. So take delta equals the minimum of delta 1 and delta 2. So meaning to say, I'm going to choose whatever is smaller to the two deltas. And I would assume 0 less than the absolute value of x minus a less than delta. So then what happened? Take note that the absolute value of f of x plus g of x, so minus their limits, the sum of the limit here. So because this is the one we're going to prove. So minus L plus M. So this is basically the same as the absolute value of f of x minus L plus g of x minus M. And by triangle inequality, this is f of x minus L. And that's plus the absolute value of g of x minus M. And this one, this 1, this is 2. So by 1, this is less than epsilon over 2. And by 2, this is less than epsilon over 2. That's equal to epsilon. So therefore, we have proven that this theorem is actually true. So the sum of the limit of, the limit of a sum of two functions is technically the sum of the limits of two functions. Okay. So let's show an example for this. You would have the limit of 3 plus x as x approaches negative 1. Remember, this is the sum of two functions. I'd have my f of x here is negative 3. My g of x here is x. Okay. Now, what's the limit of f of x as x approaches negative 1? So this is the limit of negative 3 as x approaches negative 1. This is the limit of a constant that we have shown already. And this is technically the same as negative 3. The limit of g of x as x approaches negative 1 is the same as the limit of x as x approaches negative 1. So this is also the same corollary we have shown earlier. So this is the same as negative 1. So if I'm going to take the sum of these two, I get negative 4. So technically, this is negative 4. That's it. Okay, so we'll try another example. Let's say the limit of, let's say, 7 plus x okay, that's 7 plus x as x approaches 5. So basically, I can have limit of 7 as x approaches 5 plus limit of x as x approaches 5. So basically, this is our f of x and this is our g of x. Okay. So this is the limit of a constant. So technically, you're just copying this constant here. So that's 7. This is a limit of identity function. So that's 5. So your limit is 12. That's it. Okay, so the next theorem that we will have to discuss, I'm going to show you is the limit of a product of two functions. So meaning to say that if the limit of let's say this is f of x as x approaches a is L1, and then the limit of g of x as x approaches a is L2, then the limit of f of x times g of x as x approaches a is the same as the limit of f of x as x approaches a times the limit of g of x as x approaches a. And technically this is the same as L1 times L2. Okay, so there's also a generalization for this by this theorem, like what we have done earlier for the sum. So there is a generalization for this. So if you have the limit of f sub 1 of x as x approaches a is L1, and so on until you also have the limit, the limit of, let's say, fn of x as x approaches a, and that's ln, then the sum of the, the limit of the product of fi of x, I from 1 to n, as x approaches a, is basically the same as the limit, is basically the same as the product of li, I from 1 to n. That's okay. So to see the proof for that, let's say, let's epsilon be greater than 0. Then by that, then there exists delta 1, delta 2, and delta 3 that's greater than epsilon, such that in this case, you'd have f of x minus, what happened? It should be L1 here. So less than epsilon over, in this case, we don't know yet. So let's assume this is the blank space here for, let's say this is epsilon 1 whenever 0 less than the absolute value of x minus a, that's less than delta 1, and you also have g of x minus, your g of x is L2, so that's less than the epsilon over 2 whenever 0 less than x minus a, and this is less than delta 2. Okay, you might be confused why I am actually adding another inequality here. I have g of x minus L2, and that's less than 1. Whenever 0 is less than x minus a, less than delta 3. So you don't have to worry. This is not actually in conflict with the previous statement. Technically, because you cannot assume that epsilon over sub 2 is 1. Technically, because they have different cases here. This is for delta 2, this is for delta 3. So the purpose why I'm doing this, because this statement, this last inequality, will imply that if you have g of x here, this is equivalent to g of x minus L2 plus L2. And by triangle inequality, I would get g of x minus L2 plus the absolute value of L2. And this is, remember, this is less than 1. So this is less than 1 plus absolute value of L2. So whenever 0 less than x minus a less than delta 3. Okay, now I have 3 types of delta. So in this case, I'm gonna take my delta to be the minimum of delta 1, delta 2, and delta 3. Therefore, so f of x times g of x minus, what are my limits? L1, L2. So basically, I can be able to write this as f of x, g of x minus, I can write L1 g of x plus L1 g of x. So basically, I'm adding 0 here. Okay, so this is just equal to 0. And minus L1, L2. Okay. And technically this is less than by triangle inequality I can separate them. So I have absolute value of f of x, g of x minus L1 g of x. This is also absolute value of L1 g of x minus L1 L2. Okay, and I can extract, by the way, the g of x here. And so I have absolute value of f of x minus L1. I can extract here L1. So I have absolute value of L1 times g of x minus L2. Okay, so that's it. Now, my g of x here, remember my g of x here is less than 1 plus L2. So I would have 1 plus L2 here. So that's it. And remember, this should be less than epsilon 1. So therefore, I would know that my epsilon 1 here is, so I'm going to label this as, so I would know that my epsilon 1 here is technically epsilon over 2 times 1 plus absolute value of, what is this? It should be L2. Okay, so in this case, I have epsilon over 2 times 1 plus absolute value of L2 plus my L1. My absolute value of L1, of course, that's the same. That is always less than 1 plus absolute value of L1. Okay, so this also, I can have epsilon over 2 times 1 plus absolute value of L1. So I would know that this epsilon over 2, this is epsilon over 2 plus, times 1 plus absolute value of L1. So therefore, this will be cancelled, this will be cancelled, this will be cancelled, this will be cancelled. And so I have epsilon over 2 plus epsilon over 2, and that's equal to epsilon. Therefore, technically, the theorem is actually proven now. You end up having an epsilon. That's it. Okay, so we will apply examples for that. Okay, so let's consider. Okay, so let's consider, for example, I have the limit of I have 7x plus 11, and then minus 4x plus 1. This x approaches negative 2. Okay, so in this case, this is my f of x. This one here is my g of x. So I can take a separate for that. So I have limit of f of x as x approaches negative 2. So that's basically limit of 7x plus 11 as x approaches negative 2. If you notice, this is a linear function. So we will use the theorem earlier that we just have to substitute negative 2 to the x. So I have negative 14 plus 11. So correct me if my computation here is wrong. So this is negative 14. So that's 7x, so that's, you substitute negative 2, so negative 14 plus 11, so you get negative 3. Also, the limit of g of x as x approaches negative 2, so the same as the limit of negative 4x plus 1 as x approaches negative 2. So substitute negative 2, that's 8 plus 1, you get 9. So therefore, this one here, this is equivalent to the product of this one and this one. So you'll have negative 3 times 9, so you get negative 27. That's it. Okay, let's try another example. The limit of 5x times 3x minus 5 times negative x plus 2 as x approaches, let's say, 3. Okay, now in this case, this is your f sub 1 of x. This is your f sub 2 of x. This is your f sub 3 of x. So what happened? This is the limit of f sub 1 of x as x approaches 3. So this is limit of 5x as x approaches 3, and that's, what is this? The previous theorem tells that this is 15. Okay, another is the limit of f2 of x as x approaches 3. So that's the same as the limit of 3x minus 5 as x approaches 3. So this is the limit of a linear function. So you'll have 3 times 3, 9, minus 5, you get 4. Lastly, you have limit of f3 of x as x approaches 3, and that's equivalent to limit of negative x plus 2 as x approaches 3, and that's negative 3 plus 2, it's negative 1. So you take the product of this is 60 minus 1, that's 59. So therefore, the limit of this, the product of three functions is 59. That's it. Okay, so the next theorem, I'm not gonna prove these theorems actually because there are actually consequences of the theorem for the limit of product of functions. But if you are really interested for that, you can comment down there so that I would know and I'll give you a copy for the proof for that, or we can discuss this in the next video. Here, the first theorem says that if the limit of f of x as x approaches a is L, and n is any positive integer. So I would shortcut this symbol instead. So your n is any positive integer, then the limit of f of x raised to n as x approaches a is L to the n. And this is theorem 1. Theorem 2 is if the limit of f of x as x approaches a is L, then the limit of f of x, the nth root of f of x as x approaches a is equal to nth root of L. This, however, has condition provided L is greater than or equal to 0 and n is a positive integer, or L is less than or equal to 0 and n is positive odd integer. Okay, so these are two conditions for applying this theorem here. So either your L is greater than or equal to 0 and your n is any positive integer in general, or your L is less than or equal to 0. It is acceptable in the sense that your n should be positive odd integer. Otherwise, I have explained this to my previous video that otherwise, if L is less than or equal to 0 and n could be a negative integer, then your result is not a part of a real number system. So the expression is undefined. Okay, lastly is what we call the limit of a quotient, which simply tells us that this is the quotient of limits. So technically, if limit of f of x as x approaches a is L, and the limit of g of x as x approaches a is m, provided in this case here m is not 0. So when I say m is not 0, automatically the limit of g of x is not 0 as x approaches a. So the limit of f of x over g of x as x approaches a is basically the same as taking the limit of f of x as x approaches a over the limit of g of x as x approaches a is the same as L over m. That's it. So these are three additional theorems that I want you to show the proof for this. So I'm giving you an exercise to show the proof of 1, 2, 3 here out from the style and method that we have done on the previous theorems that we have discussed. Okay, so we will show the answers for these examples using the previous theorems. So number one, we will have to solve for the limit of 2x minus 7 raised to 5 as x approaches 5. So this is the theorem that we have discussed for the limit of f of x raised to n as x approaches a, and you end up having L to raised to n. So meaning to say that we are only interested on getting the limit of this. So what's the limit of that? The limit of 2x minus 7 as x approaches 5 is 10 minus 7, that's 3. So basically this is 3 to the 5. That's it. Okay, another. This one here is you can treat this one here as your f of x, and this is your g of x. Let us assume that okay, yeah, that's the thing. So let's assume that these are actually the products of two functions. So we can use combinations of techniques. So first is we can use the theorem for the product of functions. And then we can use a theorem for the rational exponent of function. Okay, so in this case, let's solve for the limit of f of x. As x approaches -1, so we can apply also the limit of a linear function in this case. So you have limit of 3 plus 2x to the 3 as x approaches -1. So basically, we only have to take the limit for this. So linear function here, so that's -1. So that's 1 raised to 3. So that's 1. The limit of g of x as x approaches -1, that's the same as limit of x minus 2 to the 5. This is x to the -1. So that's -3 to the 5. Okay, so that's 81 times 3. That's, correct me if I'm wrong, this is 243 negative. So let's say 981 3 24. Yeah, I'm correct. It's negative 243. So therefore, the product is, the answer here is negative 243. That's it. Okay, so for number 3, what we have to do is we only are interested to solve for limit of 2x plus 9 raised to 3. That's x approaches 4. So this is the same. We can have this as this is 8 plus 9. You get 17. So that's 17 raised to 3. So technically, this is the same as fifth root of 17 to the 3. And This one also here is the limit of the cube root of 8 plus 21x. So you'd get cube root of 8, and that's equal to 2. And this one here is you have to take the limit of, so this, you can treat this one here as your f of x. You can treat this one here as your g of x. So meaning you have to make sure that the limit of g of x here is not equal to 0. So in this case, the limit of x squared, as x approaches 1, it's technically 1. The limit of 2x plus 3 as x approaches 1, that's basically 5. So therefore, the answer here is 1 over 5. So lastly, you can have the limit of the cube root of x as x approaches 8, and you also have limit of x minus 7 as x approaches 8. So you have to make sure that this one here won't be equal to 0, the limit of this one here. So technically this is 2, this one is 1, so your answer here is 2 over 1 or 2. So therefore that's the limit of the function. Okay, so that's all for now. Thank you so much for watching. So if you have any questions or clarification, you can comment down there so that I would know and I will be able to discuss. If you think I miss or there might be some errors in computation, I would also know so that I can correct that on my next video. And if you think that my examples are just too few, kindly let me know so that I can give you further examples for that. And by God's grace, of course, I will still continue with these videos for mathematics blogs because my purpose is just to help the online classes in different areas in math as long as I can. So if you have any questions or clarifications, or if you'd like to request a topic that we will have to discuss here, kindly let me know. So for those who are new to my channel, please don't forget again to comment down there, click down there to subscribe. And that's all for now. So thank you so much for watching. Have a great day.